Okay, hi. Let me start with this video on the introduction of microcontrollers, talking about the basics issues on I/O, right? Which is equivalent to go and read inputs, which are the values of input pins, and how to translate variables into output pins. That's the basics of it, okay? So the first project on this series on microcontroller is going to be about basic input and output. And to do so, as you know, we will rely on the circuits that we already have studied before. In this way, we don't have to bother very much on what they have to do, you know. For example, here in P9, you know that it is about a one-digit BCD adder, very much like the circuit that you know from P3, the other 4-bit. This time is basically the same thing. The truth table is not going to be that different, but this time is going to add in BCD to make it a little bit different. But you know, this is the idea, but in the objective, the goal of this introduction is to talk about pins. For example, how to do that thing of connecting the carry out of a basic adder to the bit 3 of the port C. Or how to do that thing of reading into the bit 1 of the port B of the A1 from the operand A, you know, how to do that. And that is something basic, because that is going to allow you to capture signals from the external world and then to do the opposite, send ones and zeros from the internal memory of the microprocessor to a specific pins for lighting LEDs or running motors or whatever, okay? So that's the basic stuff. And you know, to do that, we start always in the same way. So not solving precisely this one-digit BCD adder first, but going downwards to the section on learning materials and tutorials, because here is when we are going to find basically one step after the other, you know, step by step, the full tutorial of one example or several examples to do them all the same way, you know. And this is what you've got here in this tutorial on a similar circuit, another combinational circuit, but this time on a dual MUX 4. Okay, so that's the idea. You have this tutorial in green because it's complete. So here you are, everything. A real chip, the 74153, this time, you know, solved using a microcontroller. So the input and outputs of the channels and the enable and the Ys, the outputs have to be connected somewhere. In this way, you are going to make it a little bit more complex than usual, right? Let's have a mix of things. For example, the channel 01 is going to be connected to the pin 5 of the port A, but the channel 00, it's going to be the pin 3 of the port B. Just complicating the things like that is what I require here for you to get aware of what is on stake now when you try to pull the input pins and convert these voltages into binary variables, ones and zeros. So, you know, as usual, you have a project that can be solved very well in VHDL, but this time is going to be by means of software, using a hardware platform that is a commercial microprocessor. All right? The same way, if I had told you to solve these using the Arduino platform, is the same thing. Another microcontroller, but the same idea in mind. So the first thing that we can do here is, you know, go back to the truth table that you know very well from P3, you see, or P2, because this is a logic circuit. The other one was arithmetic. This is logic. So, you know, you have it all here explained in this whiteboard, the truth table and the symbol. And here you've got it repeated. The symbol, you see this way, that is the very best way you can go through this. In paper, this is the symbol and this is the table, you know, nothing to say. If the chip is enabled with a 0, because the enable this time is active low. If the chip is enabled, the value of the channel 2 is going to be copied to the output like that, okay? Very simple. So the planning has to include, first of all, the picture of the microprocessor, because this is what we are going to use as a hardware platform to solve the problem. And the design steps has to be, this time in this way. First of all, an schematic, because this is what you have to do here. You have a microprocessor, so naturally you have to add to the microprocessor an oscillator and a power and reset to initialize the program memory to the program flash memory to the initial position and let the microcontroller go instruction by means of the program counter, solving, the instructions in assembler one after the other. And then the power supply connections, because this is nothing but another digital circuit that has to be connected to the power supply naturally, and then some pins from the ports are going to be connected to the channels and selection and enable, and then some of them are going to be the output Y. So that is the point. And this is the capture that later is going to be converted into a Proteus file, for example, a PDS PRJ, right? So in one hand, and this is the way to work here, you have two hands. So in one hand, you have to write down the schematic, and then in the left hand is, the software schematic, the point, okay? That's the point. So it goes like that, 1 and 2. All of these projects now in chapter 3 are going to look like this, you see? Hardware schematic in one hand and software schematic in the other. And the software, it's going to be all the time the same way. The software organization is going to be like this. For example, specifically now for these simple projects, it's going to be init system, read inputs, truth table, and write outputs. And then an infinite loop around this read, truth table, and write. While initializing the system only one time after the clear direct or the power on reset. That's the general configuration of the software. So the main ideas are going to be here, not in the two table section, because this is something simple that you have to solve very easy. For example, interpreting behaviorally the two table that you got before, you see. If enable and channel or cell equal 2, then y equal channel 2, and then you can say an else if, and things like that. So the truth table is not the complication here, but maybe difficult for you to read and write, specifically if the bits are not ordered and if they have to go to different pins in different ports. So how can we are going to solve that? Well, very mechanically and following the same strategy all the same time, right? For example, here you are a lot of inputs and outputs. So the first thing that we have to do is to read a single pin. For example, the enable active law. Read the pin and go out of the read input function having what we are going to need all the time so that the two table can be solved. And what is this? This is nothing but a RAM variable. So the enable active law, and active law is because the way you have connected the switches of the push buttons, or the push buttons, this active law is going to be converted in something the same way all the time. For example, a variable var E, right, which is going to be 1 when someone clicks the button to enable the chip. That's the point, okay? So that's the first thing that you have to do. Forget, and I know that that is complicated because you like to solve that very fast, and that is not the point, okay? Take it easy, take a single pin and try to convert this pin, now an electrical voltage, into a RAM variable into the microprocessor. And so you can place nothing in the truth table and nothing in the write outputs, and simply these read inputs devoted completely to capturing the enable active law value. That's it. And in this way, you can go advancing. For example, here, because you have the hardware and the software, you can compile the software even if it's that simple, and you can run the simulation here. It is going to be very simple because you only have to have in mind the capturing of the enable active law. And in this way, you can go watching the variable in the memory and be sure that what you've been doing for capturing or pulling the value of the enable active law works. That is what I say here by a step-by-step approach. And only when this is going to work, you have to go to the next thing to do, which probably is get a couple of these pins, for example, the channel 3 or the selection inputs. Okay? But later, first of all, you have to solve a single pin, the pulling of a single pin, right? Okay, so what goes next? You see, we have simplified very much the truth table and the write outputs. You have said nothing about them, just the name of the function, nothing inside, just a semicolon if you like, not at all a single instruction, and something very simple in the read inputs. But, because the microprocessor pins can be both, you see, they can be bidirectional, you see. All right, the first thing that you have to do is to configure in the init system at least this pin, the enable active law. This is what you have to do, okay? And perhaps this picture can help you, all right? For example, in the PIC family of microprocessors, every port has a companion, and this companion is the shadow register that these people call trees. So the port C, where you have connected in the pin number 3 the enable active law cable, you see here, this is what you are presenting to read, is associated bit by bit with the trees C register, in a way that writing in this register 1, this pin becomes an input, and writing into this pin a 0, this pin becomes an output. So the mechanism that we will follow will be identify the inputs in the port with a 1 and the outputs with a 0, and then the unused pins, the pins that we don't care about, are going to be set by default as outputs. Okay, that is the configuration that we will solve here. Pin by pin, for example. So here, even it is indicated the channel 1, 1, and 0, because those are the pins 7 and 6. If you like, you can annotate now 0 and 0 as well here. All right, so a single 1 in the bit 3, because this is what we are going to consider the single input of this example. And if you have this idea for this function in its system, this is what are you pretending, this is your goal, simply to write a 1 in the pin 3 of the trees C and initialize, the port, and then you have, you may say, immediately the C code. So the C code is going to be this port C initialization, which may be solved basically, stating port C equals 0 and latch C equals 0. So what you see here as 0x is hexadecimal. In this way, you can just pack the number, this number, as a hexadecimal value, 0x. Or if you like, you can expand the full byte, 0b, this is binary, so when you say 11001000, this means, or 0xC8, because this is the code C and this is the number 8, it is the same information for this literal. All right, what are you implying here is that you are going to write into this memory position, this register, the value what is of your interest, the 1 in the bit 3. All right. So that is the function of the init system. And then I can go continuing explaining this, I can continue explaining this because we have a job to do, you see? We have a job to do here. For example, we have to read the pin enable active law and try to convert it into something useful and with utility for the truth table. And what is that if not a RAM variable, a char type, for example, with all the bits to be zeroed, excepting the bit number 0, where we are going to place the value that we have read. That's it. Okay? So this is the code. All right? A single byte of RAM memory, which is going to be, wasted, if you like. 7 bits of the 8 are going to be wasted for nothing, but that is not a problem because the microprocessor has a lot of bits of memory, at least a lot of them for these simple applications. So the goal is going to be translating what we are going to read in the bit 3 of the PORC into this convenient variable character variable, bar E. All right, and in addition to this, we will transform this value to be active high to make it even simpler, okay? All right, so the active low and active high in the end is going to be something, an electrical detail, but it's not going to interfere with the software. The software is going to be the standard logic function or truth table of a dual MUX4. So you see, if this is the goal, right? Well, I guess that this is not going to be that simple. You probably have to do that kind of flow chart consisting of a series of bitwise operations in a chain, one by one. So take it easy because something like this, reading a simple pin, may be structured conveniently like this series of 1, 2, 3, 4 operations. What kind of operations? Well, binary operations and bitwise, bit by bit. For example, why don't we go and do that kind of thing all the time the same way? That is going to have advantage because in this way it is easy to learn and easy to replicate. So now, this EETAC, which is the software, is not going to be difficult if you do that all the time the same way. So the first thing you fix in your paper what you want, which is your goal, and then you go repeating the same approach all the time. For example, here, and you can use different colors and all the time the 2 or 3, drawing tools that are going to be of interest here. You see? A rectangle is going to mean an operation. Sometimes later you will require rhomboids, naturally, for if and if else's and the like. But here, because it's something that mechanical, just operation, one after the other. So, for example, you are going to do that thing of reading the complete PORC, all at the same time, all the bits, even if you are interested only in the bit 3, doesn't matter. You get it all. So, the bit 7 has something, the bit 6 has something. You are not interested in it, you don't care, but you've got something from the poor pin. Very well, so that goes to a convenient variable bar buff. Okay, a buffer, a memory position, pretty much like the bar E, which is where you are going to save the final result. But now a convenient char variable to save partial results and be able to operate with these partial results and, mechanize the operations. For example, the next thing to do is very clear. What you do not have a single interest in the pins that are not the pin 3. So what you can do is masking this. You see, you can AND bit by bit with a specific number. For example, 00001000. In this way, you have a result. If you have a AND 0 and whatever have you captured is 0. So in the end, you have 0 everywhere except in the position of the bit 3, because 1 and with whatever you've been reading here is whatever you've been reading. That's the point. So you see, this AND bit by bit is what can be translated into C in the blue annotation here. Bar buffer is equal now to the previous value bar buffer that, remember, was simply the copy of the port C, that is the polling instruction of the port, and now AND. The AND is a simple ampersand with a literal value. You see here the literal value is 0B and the mask 0 in all the bits except 1 for the bit 3. That is the point. So now the current value at this stage of the bar buffer becomes something like 0000, whatever you have captured, and 000. All right? So now, if you like, you can do something else, like inverting and make it active high. Why not? How are you going to do that? Well, everybody knows now at this point that you can operate like this. If you have a not in mind, okay, to convert the enable active low into an enable active high, you can just operate like this with a gate short, but all the time with 1. In this way, for example, 0 short with 1 is 1, and all the time the same way, okay? But here you know nothing about this, because EEL, it is something that you've been reading. Short 1, well, in principle is E, okay? So it's E. It means that is the not value, right? A short with a 1 is generating, it's converting the short into a not. You know that a short with a 0, remember that from the previous chapter when we used that strategy in the other subtractor in choose complement. A short with a 1 was for generating the not version of the vector. So here is that point. That is the point. Okay. With the short with a 1, you have the not bit by bit. All right. And the way to annotate this short is with this symbol, you know, this symbol, like when you are using a calculator and raising numbers to a given power. That's the point, okay? This special accent, that is what is used as a short in this C. So you've got something which is, you see now, because everything was zeros, now everything is ones, except the L that now becomes E. So then you have to do the same. You have to clean all that ones. So you can do that again with a AND, with another or the same mask than before. So if you AND now this partial result with everything is 1, with the AND with 0, 0, 0, 0, 1, 0, 0, 0, what you get is exactly what you had before, but opposite. You see, instead of EL, you have an E. And finally, this is almost what you want, because remember that what you have in mind is that E to be the bit 0 to make it easy. Okay? So this variable may be simply 0 or 1, even as a decimal number. There is not going to be anything but a 0 or a 1. So here you can do that, you see, in this way. Look at this. You can go and shift the bits one by one to the right, as if you had a shift register and 3 clocks, you see? And organizing a right shifting with the S equal, remember the chip in the project 7. We talk about counters and shift registers. So we can do that. That is the point. We can do that here because the microprocessor very well can shift bits to the right and to the left and rotate conveniently a variable. All right. So this is what we want. The E that now is still the bit number 3 to become the bit number 0, but everything the same. So this is what we have to do. A shifting to the right 3 bits and filling in, you know, remember the idea of right serial input, so let it be 0. So in this way you are doing this of filling in zeros from the left and moving the bits one by one to the right. So 3 times is what you are requiring here. So in the end, the E becomes what you want. So that is the final result expected. So you see, the last operation here is that kind of shift right 3 bits. And now, what goes here is the translation of this bitwise into C. So the first one was the not sure, but with this mask, which is this literal, which is 0xFF, you see, it is a not, bit by bit. And then, well, you can do that in many ways, naturally, but I'm explaining you one way, so that's a good thing. You know how to do it, even perhaps if it's not the best way. It doesn't matter. In the end, you know a method to do it. Then, you know, you have an AND with the mask, and then if you like to go shifting bits to the right is that instruction. You know, the greater than 2 times. So greater than 2 times. This means shifting. Bitwise shifting of a specific register, and the specific register is this RAM variable bar buff. So you see, you have a convenient buffer here, bar buffer, which first of all had a value, the port C, and then you go modifying all the time the same variable, and in the end you do that thing of bar E equal to bar buff. In this way, the final result, that one where you see the bits in green, is copied to the final position bar E. That is what on stake here. You see, it takes a long while to explain, but you know, you can go using that once and again. All right. And the most important thing, like you see, perhaps, is that now, after this job has been solved, the bar buffer can be used again if you need it. There is no need to define bar buffer 2 and by buffer 3 and by buffer 4 for other processing instructions. You can reuse this variable because it's for such, right? So that is what we understand by reading. All right. Then the tutorial continues with writing and etc. And then the tutorial shows you the full set of RAM variables once all of them has been read and all of them has been written to the outputs and everything, you know. So in the end, you go following here with the to table, and in the end, you have the final program, and you can go developing. But you see, the point is that you don't have to do that in a sequence. As I said before, the most important thing, perhaps for you, is to try this. Let's try these 1, 2, 3, 4, 5, or 6 instructions in C. Let's develop that code, all right? And let's see if it is going to work or not. All right, in this way, once this is working, you can continue the tutorial, for example, writing something. But because these 2 operations don't have to be solved at the same time, and you can even solve first the writing before the reading, if you like, or one student can be solving the reading and another one can be solving the writing at the same time. Why? Because here you can simulate the values of the variable bar y, and you can imagine that the values here can be very well translated into the corresponding pin. So that is going to be another tutorial, which is the continuation of this one, only once what we've been explaining here works for real, right? Okay, so if we like to go and develop what we've been studying here, the capturing of the enable input, we can go here and the development section and organize a virtual desktop environment and save this into your corresponding folder. Save the list, the link as, you know, CSD, and now P9, and here you better invent a new folder, for example, dual MUX4, okay. and you can very well go into this folder and save the file from the web, which belongs to the hardware. And then down there you can find the same software for this microprocessor, PIC 18F4520, so you can save it the same way. Save the link as in the same folder, so now you have both the hardware and the software. So now you can go back to the unit, okay, and here in this unit you can go into the folder, and why not, it is time for running the hardware to see what is going on, you see, and at the same time now is when you can investigate the software as well, right? So here you are, it's a full example, completely solved, but here you are, the function prototypes, and then the full list of variables, okay? And also the auxiliary variables that are going to be used for saving partial results, okay? All right. So one thing to do, if you have this circuit in mind, okay, just trying to capture the enable input, is to go to the, you can go to the chip, you know, okay, to the software, and why not? You can delete everything except the variable E, or comment it as you like. You see, you can make that disappear from the software, and this is something that you do here in edit. In this way it is indent, it is marked as well, let's do it in another way. Let's do it in the environment, in the software environment. You can make changes here, right? It's not a problem because this is a text file, but perhaps the best way to do that is in the environment, okay? So let it be like this. So perhaps there is a thing to do here, first of all, is that to try to run the full simulation of this example and try to see that you get no errors at all, right? So that is perhaps the best thing that you can do if you download the file from the web. So now it's time for running this MPLAB-X IDE, all right? On the other hand, you have the hardware. So the hardware is going to look like this, as the pictures that you've seen in the web. And so inside if you go to the child sheet, you have the microprocessor. The microprocessor has no code now. You see, this may be delete. You have nothing here. Okay, nothing. So soup. You have no software now. And you can imagine that the processor speed, because this is simulated, is not the real clock that you see, the real oscillator that you see in the schematic. Doesn't matter the value you've got here. What is important here is this parameter, processor clock frequency. So you can leave it like that for megahertz, but now the program is not really here. Okay, so you say okay, and you go to the top, and well, you can see that thing of that. The only interest that you have to have here, but for now, is that is this picture. You see, the enable is connected to the port C, bit number 3. That is the single connection in which you have interest in this first tutorial at all, right? Forget the others. The others can be like this or can be disconnected. If necessary, later we will disconnect them all. So this is the second, okay? So very well, let's go to the software environment and let's switch off the windows that are not of interest. And now with a blank project or a blank space here, we can do that thing of new project. So it's going to be a standalone project. You say next. It's going to be for the PIC. You see, you can just type in the name of the microprocessor, or you can go browsing by families. The one that we are using is called Advanced 8-bit MCUs, right? The PIC 18. And here you can find them all listed. All right, but if you want to go speeding this filtering, you go and say pick 18F45. You see here, have many of them. And then if you say 2, just 4 of them. And finally, if you say 0, that is the one that you are going to use, the 4520. So now it's next. Now it's time for the hardware platform. The hardware tool is going to be the ICD3. Okay, doesn't matter very much because we are going to keep that in the simulation level in Proteus. So, but later on, if you like to go prototyping, it is good to know for you if you are going to use a PicKit3, for example, or the ICD in Circuit Debugger 3 or the PicKit3 as the tool for programming the hardware. But not now. Now it is the same, right? So you say next, and now you have to pay attention to the tool chain, which is the compiler. That is, yes, what you have to pick up, the XC8 compiler. You say next, and finally is your turn to do the usual, which is going to the folder CSD, okay, P9, that's it, P9, and here you are the dual MOOCs, and this is the location of the project, okay, dual MOOCs. So you say open, and now you have to invent the name of the project, but it's as usual, the name of the device and the construction underscore PRJ as usual. But you see this time Microchip invents this new folder inside this .x extension. So let it be the main project and say finish now, right? So in the end, you will have the project with nothing in it. You see, it takes a while to open the project, even if it is empty. But now it's going to be your turn to add something here, something that exists. And this is the advantage here. What exists? Yes, the hardware in one side and the C code on the other. So you see, you can go organizing the things because you can add to this project header files, text files. You can add, if you like, the hardware file is not going to be taken for anything, but can be here very well. And then you have to pay attention to the source files, because this is what of interest. You see, you have nothing at all, only the chip details, you see. But up here, you can say add an existing item. And now you see the item that exists, the C source file, is just, you see, one level above. So you click and find the dual MOOC C and say yes. Select it, and now your program consists of a single file project, as if it were Plan X, or, you know, you can remember many projects which consist of one single file. So now is your turn. You can click and inspect what is on a stake here, what is inside the dual MOOCs for C code, given as a sample. Okay? Takes a while to open, I don't know why, but it should be opening. Open. Now, yes, you see? You have a window with a text file. In my case, I have this idea all the time to change the option of the font. Okay, the editor font, to make it larger. Instead of monospaced 13, I like to use another size. For example, 14 and bold types. So in this way, the code is going to be larger, or even 18. I like this to occupy the full window, right? Or even 18. Well, doesn't matter. That's okay. You see, everything is here. So now your turn is to select the right options. And the options are just here with a right click on the project, okay? Go down to Properties. And here is where you have to say, as a global option for this compiler, that the standard is going to be the C90, and the final output file format is the COF, because this is what is required in the Proteus simulator, okay? You say apply and OK. And now everything is fine because this came from the web, digsys, so everything is fine to go and do that kind of tool, you know, clean and build the main project. That is it. Okay, so you clean, use the sweeper to clean the previous projects and now generate the compilation. Okay, in this project everything is in place. The main loop, the init system, okay, you have a lot of bits that are pre-configurations that you don't have to pay attention at all if you don't like. You see, so this pragma thing, you can skip it all, leave it as it is. And then you can pay attention, not the port A, you see, but to the port C. This is what is of your interest only. You see, the port C. You have to pay attention here that you have a 1 in the 3C, bit number 3. This is the only thing of your interest, okay? The other configurations can be forgotten or don't care about them. This is the only thing that you pay attention to, okay? The port C, bit number 3 in the 3s. This is what is setting this bit as input to connect the enable active log. Then you have the read input, then you have the write output and the truth table, okay? Everything is here. So very well. But for now, you see, it's time to see if everything is working fine. Okay, so, and this means that we can go to the hardware and do that thing of downloading the software into the program memory. And this is solved here in this simulator, just attaching to the chip, you see, by means of the edit properties, you attach, you hear, a program file. Which one? Well, let's see. The project is here. You have the dual MOOCs as the basic folder for the project, and then here you have the X. So click, and then distribution, and then default, and then production. And down there, you've got them both, the COF and the hex. So this time we will take the COF, because what we like to do is the final version, which is the purpose of the hex. Okay, the hex is for prototyping, or downloading the real configuration file to the chip. And now the COF is for debugging. You see 10 kilobyte and 2 kilobyte. This one, the COF, is larger because it is full with indications and variable names and the like, okay? The one that is going to be used for debugging. So you open it, and in this way this file is automatically assigned to the microprocessor, and you can say OK, and now you can go back to the top entity, and now you can run. Alright, to see if everything goes fine in this mixed hardware and software environment, right? So you click now run, and because the project is complete, perhaps that's the best, it is complete, you see now you are selecting the channel 3, so if the channel 3 is 1.1, the 1.1 is copied if the chip is enabled, but when it is not enabled with a 1, you see you have 0.0, so the full truth table can be inspected here. You see the information, if you select the channel 2, whatever you've got in the channel 2 is copied down to the output, that way, okay? And that's the full example that you get from the web. But now our point here is to run the debugging and pay attention only to the capturing, you know, of the enable input, so that later you can do exactly the same with the channel 0, the channel 1, and many more, even if you don't have the code. That is the point. Here you have it all, but not normally. You see? So now it's time for stopping the code and going back to the software, and now that we know that it works, we can do that thing of delete everything. Don't worry about that because everything is in the web. So you see, you can delete a lot of things, or you can, you know, mark them as, you can mark this which is not going to be in use. You see, the general interrupt enable is not of your interest. So this is what you can mark as a comment. You see, click, and now that becomes commented. So it is here, but it's not molesting you. So you can mark this as a comment. This is what I recommend you. You see, in order to focus your attention to the very specific idea of what you are doing, one thing at a time. So you see, now it looks like that you've got what you want, which is the init system, right? The first instruction in the code, init system. But init system, apart from these configuration bits, is everything is commented except the port C. That is what of your interest. You can even consider the bit 7 and the 6, because this belongs to I don't know which channel. You can consider that even not programmed now. So you see, the RC, our input, is the input, you may say so, is the input, enable active flow, right? So very well, you clear the port, you initialize it, and you configure the 3C to be an input, the bit 3. That is what is your interest only. So in the same, you may save that naturally, and you can go down. If this is possible now, you can go down. Okay, I imagine that now the program is doing strange things, is not responding, so I have to stop and retake it later. Okay, and this means that I have to go out of here and stop. So in the same way, you can do the same for the read. You see, let it be the variable of interest only, and let it be commented the others. You see, in this way, the read inputs is only concerning your bit of interest, exactly the 4 instructions that we've been studying. You see. And then the truth table. It is very possible for you to do that thing of commenting them all, and the same with the write. So you have no outputs at all. That is okay. You only have the organization of the software and nothing else. That is the good thing, and this is what I like you to do when I talk about developing and testing at the same time. Let's develop from this example only the variable of interest. All right. So now that you've got the hardware in one side, okay, and the software in the other, now if you like, you can do that thing of clean and build again. It has to be with 0 errors, everything right. You see, you have a shorter program, naturally, you see. All right. And you can even, it's not necessary, but if you don't like to use, you are only using 2 bytes of memory. So if you like, you can do that thing as well. I have forgot before. You can comment this variable, which now is not required, and all of them except the E. That's the other thing. In this way, you can recompile again that thing, and now there is only in the listing, you see, 2 bytes of data space. The memory has only 2 bytes. That is good. This is exactly, you see, that kind of control is what you have in mind. All right. So now what has happened is that you have a new configuration file downloaded to the chip. So now you can say run, okay, and nothing is going to run naturally. Now it's not nothing here. Nothing is going to work. So now is when you can just do that thing of going to the step-by-step mode. You see, instead of clicking play, you click the other one here, and 2 windows has to appear by default. The source code and the CPU variables. And here is where you are going to identify the bar buffer, the 3C, and the bar E, the final position where you are going to save the variable. Very well. And if you, by any chance, you see, kill this window, if you close it, no problem. Don't panic, because, you know, these are the windows that you get through the debug tab on the top. So debug, you see CPU, and here you are the option to get again the source code window and the variables window, along with many more. So this is the source code. Okay, in this way you can go doing this step by step. You see, look at this. Look at the way the machine is executing the infinite loop all the time. It's initialized and now it is executing the infinite loop. So you can have this window and then the other one, which is the list of variables. So you have them both, right? So look at this. You can run continuously, but in this way you see nothing because the program is not already finished. But what you like to do is to go and run step by step and execute one instruction after the other, going over the instructions or going into the instructions. You see, you have different possibilities here. You can go into the, for example, now that you are pinpointing the read inputs, you can go into the function, and now this is the point. The only instructions that are going to be executed are the ones that you have left belonging to the capturing of enable active law, right? You see? And then in the end, the machine does what you want, all right? And that is very important here. You are commanding the debugging and developing, not the machine. So in this way, you can go finish with this work and then add one thing at a time and doing the same revision, the same recompilation, and the same mechanism of step by step. And now, you see, if you go step by step, you have this list, but that is not that convenient, right? It is 1,000 times better to go to the book and get what is called a watch window. So that is what I like best here. And this is essentially why we pay this software for, right? This is what is valued. You see, you have something very interesting, which is this idea of dragging the variables from the variable window to the watch window. And here you can see the evolution of everything in time as long as you are executing instructions. You see, you can you can see them both all. So very well. Now that you've got the watch window, you can do something like this, run continuously, and so like that you have this variable. This is the address of the memory position, which is not of your interest, so you can switch that name and value. And because here we have an interest in binary values, you can replace that. You see data type, and it is a char naturally, but the display format is going to be binary. And you can change the font as well, right? So let's change the font to make that variables larger. So set the font, and so for example 14, okay, something like this. So now the machine is running, and what is happening now? Okay, what is happening here? Well, because the machine, you see, the machine is stopped, you see nothing, but when you run continuously, what you've got here is the watch window, which is equivalent to spying. You know, you are spying the internal content of the RAM memory, which is what you want. All right. For example, if you read, you can see now what is going on. The system is running, right? The bar buffer, you see, is changing values because the program executes the code. It takes, if the clock, you know, the oscillator is 4 megahertz, the simplest instructions, or the most of them, take 4 clocks to be executed. So in 1 microsecond, you are executing one instruction. So the program now is running in a way, more or less, executing 1 million instructions per second. So bar buffer changes because, you know, what you do with the bar buffer is apply some mask and then shift, and naturally the bar buffer is changing very fast the values. Okay? And so look at this. The port C changes the value. Now it's capturing a 1. So this is what you call sample, right? You sample the port B, and then you move that data just not to the final position, which is the variable E. So you see that thing? All right. What else is what you can do here? because now you have the environment to investigate more things. It's not necessary to do that all at the same time, but perhaps that now we are here, we can ask a question. For example, how many samples per second, or how many pooling, how fast is that system? Okay, how many values per second are taken from the enable input active law? Okay, how many values are taken per second? That's a good question. So to solve that, you have to go and step by step, and you know that because the machine you see is running continuously, you may like to go into the read inputs, for example, and place what is called, you see, this is the code that is saved in the ROM program. So you can, by the way, if you like, you can see what you see now is the C, but you know, with a right click anywhere here, for example, you can just disassembly. In this way, you have the code in C and then the real code in assembler that is executed. You see, you have a no operation and then you have a move. Move means move this value 0001 to the working register, okay? And then you see AND, so that is what you say here in C. At this level, this is a very low level instruction. It is practically the same that you find here in assembler. So the compiler is not working very much here, simply translating the C syntax into the assembler syntax. So this is what I say here. Every one of these instructions in assembler takes about one microsecond, because the clock is 4 megahertz. Okay, if you have a faster clock, the time to execute a single instruction is less than that, right? It's shorter, naturally. So if you have a given instruction in C, for example, you can do that thing of click now on the left, and this red cycle is what is called a breakpoint. So this is going to allow the program flow be stopped here. Okay, the code is going to be broke and you will stop here the execution of the code. And what is the meaning of this? Well, because you are in an infinite loop, okay, you can run, you see, and when you run continuously, the machine is advancing in time. Look at this down there, the indications, you see, the time is advancing. You have 104.75 seconds, you see, but 30 microseconds has elapsed from the last time when you click. Alright, so if you run, you see, you have now 27 microseconds. Guess why? You see, and again on the breakpoint. So if you run, 30 microsecond has elapsed. And why these values and how so? You see, if you advance now a single instruction doing this, click, you see now you are in the next instruction, and if you say run, you see the machine will stop again into the breakpoint. So you say click, and now you are, 27 microseconds has elapsed. All right. Let me do it again. Click. Exactly, 27 microseconds. And why that time? Okay, that is the time that takes to run the complete loop. All right, and why not 30 but 27? Because here you are executing probably several instructions in assembler. Okay, and if you disassemble now, you see 1, 2, 3 instructions. This is what I said before. You see, to execute one instructions, the system takes 1 microsecond because of the clock. All right, and if you have 3 instructions, it takes 3 microseconds. So this is why you can run now, and now the breakpoint is at it's here. So if you run, you see 30 microseconds. By the way, if this is the speed, if this is what it takes to go back again to the pulling of the value count enable, you know, 30 microseconds. Inverted is, you see, the program runs that kind of pulling at 33,333 or 34, you know, instructions per, I mean, samples per second. This is what it takes to run. So 33,000 samples per second. Now is for you a good time to compare this with the traditional development and planning of this, you know, application using hardware. Okay. Okay, you may say later on that this is what it takes to execute the truth table. So what if a truth table takes 30 microseconds? What was the time in chapter 1? Perhaps 30 nanoseconds. So you see the difference? In hardware, you do the same product, but 1,000 times, at least, faster. But in any way, there is a way to do that, you know, a little bit faster. How? Well, you can do that a little bit faster, you know, changing the processor speed. So that is your time to do that if you like. You can go to the child sheet, and here you can leave that. Change the speed of this crystal, because this is the oscillator of the device. But you can change this speed very well here, editing the properties of the device, and for example, placing here 16 megahertz. Naturally, there is a limit, right? There is a limit. You cannot have here 500 megahertz. Absolutely not. So 16 is possible for this microprocessor. Okay? So you can save this, and now you can go back to the top. You have the same code, you have everything the same, but now the processor, you know, the computer is going to be running faster. And this means that the complete loop to the program is going to be solved in less time, right? Let's check that thing. So if you run now, okay, you are stopped again in the same breakpoint. So now if you run continuously, you see, look at this. Now 7.5 microseconds has elapsed, exactly 1/4 of the time, you see, required before, because the frequency of the clock is 4 times faster. So everything looks fine here. So this is the kind of environment that you have to organize by your own, so that now, if you like, you can go and make modifications, changing the masks, adding new bits, and you can do that here because you have it all, okay? In one hand, in the web, you have the main ideas translated in paper. So now, for example, that you've got something reading, you can add something else, like the channel 1 or the channel 0 from this multiplexer, or you can do the other thing, which is writing, okay? You can go and try to write. For example, you can invent the variable bar y, and you can try to see if all these bitwise operations are possible and work fine. All right? So very well. So perhaps before finishing this tutorial on reading, it is good for you to talk about something else, okay? Additional considerations. That is always possible. We have done something like reading an input, so it is good to, you know, to do this kind of job of looking forward and backwards and try to see if we have understood correctly what is going on here. So if you have this thing in mind, you know, this idea in mind on pulling signals, okay, you may ask yourself, how fast is the circuit as we have solved? You see, in that example, it took 30 microseconds, which means, you know, 33.3 kilohertz of, this kilohertz means 33.3 thousand samples per second. This is more or less the idea. You go and get samples from the enable active law at this speed. You see, this is what it took to run the full loop. You see, you have a loop, and then you go back to the beginning and the loop, and you do it again. And you do that all the time, so that here you have the reading function, so this instruction is executed at that speed. Very well. So how can we measure the pooling speed? So the same way that we did before, right? Using the breakpoint and stopping the program at a given instruction and running the loop. So the machine tells you exactly how long does it take. And here there is something even more important. How the sampling is going to look like. You see, you have this input from the bit 3 of the port C. You go through this function in the end, because this is the only thing that has been programmed. Everything else has been marked as a comment. So what are you doing specifically is taking samples of the value that you've got in EL, whatever it is, a 0 or a 1, you know, and then what you do is to load, you see, the bit 0 in this variable E. So very good. So how is it going to look like that? See, you have a kind of a sample frequency, but is queer, you know. It is not that, it is, you know, you've got here some kind of repeatability. Yes, it is true, but you know that there is not here, perhaps because this software is very simple and some logic instructions that all of this software has to do. But normally you will have that sometimes, you know, because this is about the software execution, sometimes the number of instructions to execute because of an if or a case or an else, you know, is different. And this means that sometimes, depending on the software, between samples, you will have a time t1 and then a time t2, and you see, it's that messy, the thing that means pooling. It is right. You get the values from the inputs, but you see, in this erratic or unpredictable way, which depends very much on the number of instructions in C that are executed. You see? So this is fundamental, because here you have a kind of a repeatability thing. You see, you get samples continuously because the loop is executed constantly, but the samples came at different times. You cannot imagine here something that was a kind of a must in the chapter 2. You see, it was a perfect sampling frequency related to the clock. So this is, here you don't have the clock anywhere. You have the possibility to get values from the inputs, but not in any way the values are sampled synchronously with something resembling a clock or the like. Okay, that's the first point. And then perhaps, you know, well, you know that this time can be shortened. It is true. You see, if as you have seen now, if you are increasing the clock frequency, what you will get is a shorter execution of every single instruction, and this is going to increase the number of samples per second. So this, in this initial, you may say, primitive software example, that is the way it works. So here we are plenty of opportunities, you see, in the next projects to come, to arrange all that. How to do that in another way, okay? More professional, okay? So the last comment here is that it is true, you see. Let me repeat that because it's not that so obvious, you see. You are executing software right now. There is nothing like 3 levels of gates or the propagation time from a clock to output, which you are an expert in calculating. That is not happening anymore. You are executing software. So the more instructions you have, the slower is the loop. And if you like to have faster sampling frequency, if you or pooling frequencies, you have to increase the crystal. Or you have to pay for a professional C compiler, because in this way every instruction in C is going to be converted into less instructions in assembly, and the code is going to be more efficient, and in doing so at the same time, because there is less instructions to execute, the loop is going to be faster, right? So this is the panorama that you can and the many concepts that are related from the very first program that you execute. Okay, so this is what you are going to try to improve in the next examples that are going to follow this initial lesson in project P9 and then P10 and the like. Okay, so you see the clock. We like to have a clock here. So how is going to be possible to have a clock? Now we can leave these very important questions in the air, so that it is going to be good for us to try to think on how to solve a clock, because this clock, you know, now that you came from chapter 1 and chapter 2, you know that the concept of this clock is fundamental for inventing reliable and repetitive and professional equipment, right? So that's the kind of introduction to the reading and pulling signals. You can do the same now with another video or just by yourself with writing. The same kind of organization, but focusing your ideas now in how to write. You've got a variable like y, var y, how to do that of translating the values that you put here in the bit 1 and the bit 0 of write var y. So now let's make that two pins changes accordingly to the value that you have here. And so, for example, if you have there connected a couple of LEDs, the LEDs can be sensitive to the voltage that you've got, right? Something like this.